But here, so you want to know the practical application. So even though you have a very decent adsorbent for CO2 capture, but from a point of practical application, you have to consider, the other points. So here, 2 points should be considered. The first one is that, so usually the MAP can be achieved in the form of a powder. But powder is okay, but that is not good for practical applications because so there is a handling problem and also pressure drop problem and reusability problems. So for practical applications, MAP powder should be converted in the form of beads, pellets, and membrane, for example. And also, the MAP actually known to be very unstable under humid conditions. But as I mentioned before, flue gas contains water vapor, 5% to 7%. So therefore, water vapor stability is one of the very important requirements for practical applications. So our research goes to fulfill these requirements, the MAP shaping and structural stability under humid conditions. Okay, here we try to make the MAP shapings successfully using several types of binders. So we tried polymer binders, etc., and we actually came up with alumina binders. So actually, from a point of process, actually alumina the Joule binder actually performs the best because actually this the shaped material should contain the guarantee like attrition index. Okay, so we use a spray dry method. Actually, this work is actually collaborated with the Dr. Yonggi Park in Crete. And then, so we were able to make this kind of, the spherical shaped composite materials with the particle size of 30 to 70 micrometer. And then, so you can see here, so this is a spherical type of composite material right here. So we can see the presence of this MAP rod on the surface and in the inside of this particle. And also structure is maintained right here, and also anti-adsorption capacity tend to decrease due to the increase of non-adsorbed the material like aluminazole right there. And then so using this shaped bead, so we actually functionalize this material with this diamine. Okay, so it's called EEN, and then we were able to make this kind of EM MAP, the shaped bead. And then again, from the CO2 isosome, we checked CO2 capacity at the 150 millibar, the flue gas condition right here, and it shows significant the CO2 the capacity so as well. And then, so we now are successful in MAP shaping. Yeah, that's good. In addition, as I mentioned before, water vapor maybe makes some problem. So it should be actually carefully handled. So actually, this shaped MAP shows the hydrophilicity on the surface. As you can see here, contact angle, no contact angle. So we actually coated this material with silane with long carbon chains right here. So, and then you can see contact angle right here, and the surface of this bead is now hydrophobic. So, we also check the CO2 capacity at 150 millibar. So this value is still quite significant. And then this same EDS data revealed that so you have like magnesium from MAP and also aluminum from the binder and also silane from silane coating. So you have everything in there. So we check the stability under humid condition right here. So you have pristine MAP and shaped MAP and silane coated MAP. Okay, so you expose these materials to these conditions at 10% water vapor here. So you can compare the CO2 capacity as a function of exposure time. Okay, so this the blue one is the silane coated bead. So compared to other adsorbent, actually this silane coated one shows the best performance. Okay, and also after the 3 days exposure, the structure of the silane coated the bead also well maintained as shown on this PXRD data. However, this material was exposed to more the severe conditions, and then we conducted adsorption desorption cycles. So what happened here is that, so you can see here, so there is a continuous reduction in CO2 capacity when this cycles goes on. To figure out what's going on here, so we measure the CO2 capacity as well as the diamine, the content in the MAP, using digestion NMR. So actually the bar graph indicate the amount of diamine per magnesium here. Actually, when you actually ran the cycles, so diamine, the content undergoes the gradual reduction, followed by reduction in CO2 capacity. So what happened here is that actually you have a diamine coordinate to the magnesium, right? And then when you heat up the sample or actually you expose this material to water vapor, actually this diamine can be replaced by water molecule, or so this diamine is subject to evaporation at the elevated temperature. So that's why you can see this kind of gradual decrease. So this is not what we want. So after get this data, we try to address this issue using this simple reaction. So you have epoxide here and nucleophile here. So after nucleophilic attack, ring opening occurred to make this kind of ring opened product. So what you need is that we have actually diamine. So you have amine group. So this amine can act as a nucleophile. So you can put the epoxide, okay, to make it happen. So here we utilize the epoxide with different carbon lengths as shown right here from 1 to 17 here. And then we reacted this epoxide with a MAP containing the amine group right here to generate alkyl amine right here. So we actually measured the CO2 and water adsorption the properties to determine what happened there. So this is the correlation diagram. So x-axis is CO2 adsorption capacity and y-axis is water adsorption capacity. So ideal region is right here. So you have high CO2 adsorption capacity and quite low water adsorption capacity because you want to get rid of water vapor. Okay. So this is an ideal one. So when you use C1, C2 epoxide with a short carbon length, so you have a very low CO2 adsorption capacity. However, you have a very low the water adsorption capacity. This is actually acceptable one in terms of water adsorption. However, not for the CO2 adsorption. So we think that so you have this kind of map, and so diamine group is right here. So you have a pre-diamine right here, toward the pore center, and then so when this small epoxide used, this epoxide can go, diffuse deep in the pore because of the small size. So therefore, this epoxide can react with portal diamine as well as inside the diamine. Okay, that's why water adsorption capacity is low, while CO2 adsorption capacity is low as well. However, when you use epoxide with the long carbon chains, due to the size of epoxide, actually they cannot go into the deep inside of the pore. Okay, so they just react with the portal diamines. So that's why you can keep the free diamine inside of a pore, and also you can actually prevent diffusion of water vapor in the portal. So we think that is what happened here. So we take actually this C17 the materials for the measurement. So right here we use C17 epoxide to modify this EN. Okay, and then you expect to react C17 epoxide with the primary amine and also secondary amine. So when you actually proceed this reaction, the product is going to be like this. So when the primary diamine is reacted with the epoxide, you can get this kind of the chemical species. Or when this secondary diamine is reacted with the epoxide, you can get this kind of the chemical product. Okay, so these products are actually confirmed by the XPS data right here. You have a tertiary diamine, tertiary nitrogen peak right here, and you have a secondary nitrogen peak right here, and you have a primary the nitrogen peak as well. So this data demonstrate that you have these species as a product. And then we check the solid state NMR right here, so you can get the additional peak intensity coming from epoxide. And then so you have to check the nitrogen NMR, showing that actually due to this kind of reaction, you have the broad range of the chemical environments. Okay. And then we check the CO2 adsorption again here. And so this is again carbon NMR, and this is nitrogen NMR. So using this NMR data, it is possible to figure out the reactions of the CO2 with the amine right here. So actually this peak in carbon NMR is ascribed to this carbonate carbon. And then you have, this peak and this peak after CO2 dosing. So this peak is ascribed to the carbonate N right here, usually created after CO2 the adsorption. And then you have ammonium nitrogen right here. Okay. So using this data, so we think that there is the carbonate species adsorption right here after CO2 capture. And then, so this is a silane coated one, and this is a epoxide coated one. Yeah. So long-term contact angle measurement indicate that the epoxide one is much better than this one. So you can see value right here. It's almost the same, but you can see difference here. And then, so water adsorption is measured using isosome data. So this C17 epoxide modified one shows almost no adsorption compared to others. So that means hydrophobicity is quite significant in the epoxide one. Okay, so and then we measured TPD, the signals. So you actually expose this material to CO2, humid CO2, and then you dissolve everything by heating. Then you can get this kind of signal. Okay, so you have a CO2 and water. So in this data, I want to make sure that, so actually this silane coated one shows the small peak of water compared to the pristine, the shaped one and silane coated one. So these data again demonstrate that this kind of epoxide coating is really successful in terms of the preventing the water diffusion. So this is actually the experiment adsorption desorption cycles under humid conditions. So you can see no change. And also we also check the diamine contents here. So there's also no change. So actually these data demonstrate again that the epoxide the modification strategy is kind of successful. So because we can obtain quite good recyclability of this sample. Okay, now actually diamine, the problem here is that diamine is replaced by water vapor and evaporated in heat. But after epoxide modification, we actually address these issues.